Recording is rolling. It is Wednesday, April 30th. You guys have your packets. We're going to focus on part C today, which is going to complete the packet. So probably most of you guys, maybe everybody's going to have this turned into the grade tray by the end of today. And then I'll start scoring these and we're going to go there. All right. So I need to recap with you guys some major concepts from A and B about bell curves and stats. Then we'll get to C. All right. Then, all right, how class been pacing out today is we're gonna have about 10 spare minutes at the end of class. So just to get one of the upcoming activities going, the last 10 minutes of class, I'm gonna give you guys this quarter page of topics on quantum mechanics, and I'll help you guys put together a quantum mechanics journal. So I'll show you guys that about the last 10 minutes of class or so. All right. And then you guys know tomorrow in the next few days we'll be doing final exam review. And so we got a little bit of the next few weeks going on. We got stats as our main focus. Last 10 minutes, we'll start on this journal, which we're not going to get to the journal until next week, but at least it'll have it started. Okay. And then for the next few days, we'll be doing final exam review. All right. So is everybody okay with the agenda, what we're doing? All right. All right. So you guys got your packets. All right. Now, remember what you guys have been learning for last couple of days. So a lot of new concepts. We've been trying to make some kind of sense of aggregate statistical data. So one of the common examples we've been using is, say, like heights within a population. Say you went around and polled everybody, what's their height? And you made a bar chart, say to the nearest centimeter, right? You say, okay, well, there's almost nobody this short. There's a few people taller than that. There's a lot of people that are kind of average. And as you get taller, it peters out, there's less and less. Stand back and look at it, and you see a bell curve emerge. Ooh, a bell curve. And if I assume this is normally distributed, there's a lot of data in the world that is. We're going to make a lot of simplifying assumptions here, including that height would be. Then I can describe any of these normally distributed bell curves with two numbers. That's to say the mean, the average, which by the way, for normal distribution, the mean, median, and the mode are all the same value. Right? And also, guys, what about how wide the bell curve is? How wide or skinny? And that, I think it's called standard deviation can tell me that. Right? You guys know the formula to get the mean. You add them all up and divide by the number. And then standard deviation had a whole square root formula. We ran one of those a couple of days ago, and then we've been using the calculator, just crunch that data. Right? Okay. And on this bell curve, the standard deviation is the distance from the mean, which is the peak of the graph, to this inflection point. You guys remember it switches concavity from concave down the middle to concave up on the tails? Okay. So that tells you, that's standard deviation. There's an equation for that. Okay. It tells you basically how wide the curve. And so everybody remember all that? Everybody good? Okay. Now, if you pick a particular value, let's say you're right at this inflection point. Would that be one standard deviation above the mean? Okay. Oh, guys, how about this question? Who remembers this? For any particular data, if you go plus or minus one standard deviation, how much of the entire population will that cover? 68%. Yeah, 68%. That's right. It's called the 68, 95, 99, 7 rule. That's plus or minus 1, 2, or 3 standard deviations. Okay. And then what else was I going to ask? Yeah, so suppose you were like one standard deviation taller than the average person. Yeah, right. Right. You can say, well, where do you sort of rank within the wider population? You're taller than what percent of people? Well, that'd be this much of the bell curve. You're shorter than how many people? That'd be this tail of the bell curve here. And for that, you can go to the Z table. You guys remember we've been consulting the Z table? It tells you how much of the graph is shaded, how much of the bell curve is shaded up to that particular Z score, which is how many standard deviations you are from the mean. All right, so with all of that, a little bit of review. You guys ready to start on part C? All right, so C. Oh, I got some formulas at the top. Here's how to find a mean. You add them all, divide by the number. Here's standard deviation. It's a whole square root formula. We're just using the calculator for that. Here's Z-score, which remember what Z-score is. It's a count of how many standard deviations are you from the mean, or is in an individual from the mean. Right? It could be positive is greater than, negative is less than. Right? And there's one new formula that we haven't actually used yet. Look right here. It's a new one. It says for a group. And that's actually the point of this whole stats part C is to start putting individuals into groups and see what happens to the stat. So according to this expression, we're going to find a new standard deviation for a group by dividing by the square root of the group size. That's what the square root of n is. So if you have a group of 100, you divide by the square root of 100. Okay, you guys get that? Okay. Right. And then here, let's go through this example, and then I'll paddle back and forth, give you guys some analogous stories that you can attach to some of these, right? But our main two stories are heights and how much water is in a bottle. And the left side, I got heights, and the right side, I got water in a bottle. Okay, so number one, suppose that the average human height, I'll call it x bar, or you might see mu, x bar mu. Now my paper says 177 centimeters. That's right there. Now your paper says something different. So you have your numbers, I have my numbers, and I have a standard deviation. I'm going to call it S. You also see the letter sigma used. I put that right here. I'll call it S of 9 centimeters. Make sure you guys are following, because if my numbers are completely true, then what's 177 plus or minus 9? Is that 168 to 186, I think? Somewhere there? Right. And if my numbers are true, then what percentage of the population would be between 168 and 186 centimeters? 68%. So 68, 95, 97. Okay. All right. So remember that. So question is, what's the expected value for the height of the next person that walks in through the door? Because it could be anybody. Isn't it completely random? Right? Now, what if you had money on the line? What if you had to make a $5 bet? Ooh, who's going to walk in through the door? We're going to measure their height. Now, to the nearest centimeter, like let's just keep whole values, right? What number do you want to write in this box that could probably maximize the chance of you winning the bet? Yeah, how many of you guys just want to copy paste that average height right there? And again, mine is 177. Yours is whatever's in that box. Okay, 177. Right? Would that be definitely the plurality of people? Right? If there's 100 people who walk into the door, probably more often than not, gonna be that. Right? Half less, half more, something like that. Okay. Right. Right. But of course, there's some variability on that, and that's the next question. What's the standard deviation? I'm just asking for this number right here. You guys see that? Just asking for that box. So copy paste that number. Right. Oh, and I left off the unit. I meant to call it centimeters. Can you guys write that centimeters out there? Because these numbers have units attached to them. Oops. Right. Okay. We got that. Right. So just copy this one. Right. Therefore, what's the percentage chance that the next person walking through the door has a height greater than or equal to a super tall height? Woo, 185. Woo, what would that be? Right. So let's get a z-score, and we'll go to z-table and get a percentage. So one thing at a time here. So z-score, you guys remember z-score was the target value minus the mean. Right. So right away you would know, are you above or below average? Right. But in the context, are you sort of average? Or are you way out on the tail, way above or below average? Well, you only know that if you divide by the standard deviation, which gives you a count of the number of standard deviations. Isn't that what z-score is? Okay. So let's throw some numbers in here. So here's my target value. What's the chance of somebody being this crazy tall or taller? Ooh, that tall. Compared to, see, the mean. So I'm going to subtract off the mean. So right away, I see we're talking about somebody who's taller than average. I'm going to give a positive z-score. But how much taller? A little bit taller than average? Crazy taller than average? Oh, I'm going to divide by the standard deviation, which tells me of course, the variability within the wider population. Throw this in my calculator and get a number for my z-score. So what is that minus that in parentheses divided by that? Okay. I'm getting a z-score. Okay. This looks okay. All right. I'm getting that as my z-score. And that's going to go in this box right here. Okay. Guess where I get the z-score? Okay. Now, keep in mind what we've been doing for the last couple of days. Should your z-score, guys, what if you run your numbers and you get, oh, I just got a z-score of 15. Does that sound about right? Should you get something probably between -2 and 2? Yeah, probably between -2 and 2. Right? If you got like 1.1, you're probably good. Okay. Should be between about -2 and 2. Is everybody good? Right. So what does that mean? Now, guys, look very carefully how this question is phrased, because there's one of two phrasings that could lead to one or another outcome. Did I ask what's the percent chance that somebody is less tall than this tall height or taller than this tall height? Taller than, right? Which tells you something about, let's go to the z table, right? And the corresponding bell curves, right? Right. Now, I have a positive z-score, so I'm looking at the right half of the table. Right? Am I looking for, guys, look at this bell curve that's shaded in. Am I asking what's the shaded in region, which is shorter than that height up to that height? Or am I trying to ask what is this white tail, which is taller than or equal to that height? Is it the shaded or the white tail? White tail. The question is ask about this white tail. What's the percent chance that somebody is even taller than an already above average height? Okay. Which, by the way, is the answer to that box going to be more than or less than 50%? Less than. Do you guys see this white tail right here? covers less than 50% of the entire bell curve, obviously, right? Do you guys see that? Okay, right. Now, what about this table though? Doesn't this table tell you the shaded value? Right? 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 So let's check out for, mine was 0.89. So go to 0.8. So there's 0.8. Remember, go across the columns. 0.80, 1, 2, 3, 4, 5, 9. 0.89 would be on the far right end of the table. So 0.8 and then 9. Right? I'm looking at that number, bam, right there. And my table of values says 0.8133. I'm going to round that to 0.81. Is that okay? 0.81? Right. Guys, what does that mean? What does it mean, 0.81? 81%. It means that, let's go back to this diagram. You guys see this shaded in bell curve? I'm shading in 89%, or sorry, I'm at 81%. I'm shading in 81% of the bell curve up to that particular height. You guys see that? Right. So back over here, a z-score of 0.89 means that the probability of being greater than is 81%. Right? Which means that the probability of less than, which is actually how the question is phrased, is equal to what? 19. Aha! Because I have to take everybody and subtract off that 81%. Right there, point. Gives me 19%, and that's the answer to that question. Right? What's the percent chance that somebody is even taller than average? It's got to be less than 50%. Turns out it's 19% for those particular numbers. Okay. Is that okay? Okay, there we go. All right, so go back to this. I'm going to write 19% right here. Okay. All right, so is there any question on the first 4 boxes? Okay. Because what we've done up to this point is actually just review from the past couple of days. There's nothing new yet, but there's about to be. All right, are you guys ready for a new concept? You guys ready? All right. So number 2, let's use the same average height and standard deviation as a number 1. Okay, so all these numbers still apply. Blah, blah, okay. What is the expected average height and standard deviation for a group of 5 people who walk through the door? Ooh, so now we're not looking at an individual anymore. We're looking at a group of people. And before we go plugging and chugging, I want you guys to really see the big picture and get this concept. So I'm going to draw a few bell curves right here, right? Because let's look at a visual version of this first. So they have frequency and height, right? Just to match what we've been doing for the past 3 days, right? I go around, pull a bunch of people, get a histogram, make a bell curve, right? Let's say for individuals, I end up getting a bell curve. It looks something kind of like this. So who's short, not too many, who's medium, a lot of people, who's super tall, not too many again, makes a bell curve, right? So this is for individuals, right? And a single individual who walks in the door, well, I'll give you anybody, right? I have no idea, right? I have a probabilistic idea. Are they kind of average height? Probably. Are they super tall? Maybe, not probably, right? Are they super short? Maybe, not probably, right? But what if more and more people start walking through the door? Let's take this to an extreme to really make this clear. What if, guys, what's the population of planet Earth? Is that about 8 billion? What if all 8 billion people of planet Earth go Congo lining through that door right now? And I measure all their heights. And I take the average of all 8 billion people on Earth. What number do I have to get? Yeah, the exact average of this bell curve. Right? In fact, it wouldn't really be so much a bell curve anymore. Wouldn't it just be like a straight vertical bar at that point? Right? So this right here would represent 8 billion people. Right? The average would just be a solid number. Oh, now just to keep things super straight, the area under that curve and the area under this curve is the same area. It's the same amount of paint, which means really this curve goes way off the page. Do you guys see it? It goes way off the page. Because the frequency would be, well, it'd be 100% of 8 billion people, right? You go way off the page, right? Right. So if this flat looking curve is true for a single individual, I'll tell you something about the variability. Here's the inflection point. Here's the mean, right? And if I had 8 billion people and I took the average of 8 billion people, I obviously get the average of everybody because it's the same thing. It'd be only one possible number, which would be the mean. You guys see you could interpolate between these two curves? So as I started to put people in groups, the average of a bigger and bigger group is going to approach the average of the entire world population, right? So do you guys think that for a group of 5, let me draw this as best as I can. I'm going to make my, okay. Do you guys think that a group of 5 might be a bell curve that looks something roughly like this? That makes sense? Okay, so I'll call this a group of 5, or maybe a group in general. It's going to be skinnier than for 1, but it's going to be wider than all 8 billion people. Right? Get a. Do you guys think that could be the inflection point right about there? Well, it's IP inflection point. IP inflection point. Right? You guys get that? Right? And why am I marking out the inflection point? Because the distance from the mean to the inflection point, doesn't that tell me the standard deviation? Right. So let's compare these 2 standard deviations for a single individual and for a group of people. Guys, which has more variability? A single individual or a group of people? And a single individual, because that could be any, right? Like, what's the chance that somebody walks in the door is like 7 feet tall? Well, probably not very often, but it's gonna happen sometimes, right? But a group of 5 people, what's the average for the average of them to be 7 feet tall? Is that almost never going to happen? So it would definitely be less variable, wouldn't it? Right. And it turns out that the math for this, and I don't know why this is, but maybe if you take graduate level stats one day, is you have to divide by the square root of the group size. Okay. Or maybe if you want to go home and Google that, if you're really into that, like, why would we? Right, so let's do that. So question number 2, what's the expected value for a group of 5? Well, what do you think the average expected height would be? Would it be the same as before? Yeah, so it's the same average, right? Notice all these bell curves. Guys, are all these bell curves all aligning at the same average right there? Same average, right? So that didn't change. The average didn't change. The center of all the bell curves is still the same, right? So that number is that number is that number. I'm just copy pasting what I got from here. It's all okay. But the standard deviation for a group. Now here's what's new. Post number 2. Standard deviation for a group is the standard deviation for an individual divided by the square root of the group size. Or whoops, I'm switching my notation. I'm sorry about that. Sometimes I use a sigma, sometimes I use an S. You guys, no, okay. So for a group of 5, I'm going to take it for an individual, which was okay. So for me, that's 9 centimeters. That's kind of my plus or minus factor. 9 centimeters. But I'm going to divide by the square root of 5 because I'm putting them in groups of 5. Okay? Good. And what is that standard deviation? Okay. So for me, I'm getting this number. Now that's still centimeters because my plus or minus factor is still in centimeters. So got a unit attached to it. Okay. And that's going to go in this box right here. Okay. Okay. So how about you guys? You guys doing all right? You guys got up to that box filled in for your paper and your numbers? Very good. Any questions? Any questions? Okay. All right. So let's finish out this story and then I'll take a pause break and give you guys some analogous stories, different ways to put this in context. Okay. So therefore, what's the percent chance that the average height of the next 5 people collectively walking through the door is greater than or equal to this already really tall height of 185 centimeters, which I used before for an individual, but now it's a group of people. Ooh, right. Now again, before we go plugging and chugging, I want to make sure that you guys get this concept, right? We're going to get z-score. We're going to go to the table. We're going to get a probability, right? But guys, is the probability of a group of people all being super tall going to be less than or equal to or greater than the original 19% that it was for an individual? Here, let me say again. I think I phrased that bad. Right. So the chance that somebody walking through the door that's super tall, a single individual, I'm calling 19%. That's about a 1 to 5 chance. 1 to 5 times they're going to be super tall. You guys get that? Okay. What's the chance that a group of 5 people collectively, on average, are all super tall? Is that going to be more than or less than 19%? Less than, a lot less. You guys see a lot less? Right? Now, I don't know exactly where we're going to, of course, get a hard number on this. I'm just going to make a guess. You guys think this could reasonably be somewhere between about 1 and 5%, maybe 1 to 5%? Okay. Okay. So let's see exactly. So let's get a z-score, run the numbers, and see why this makes sense. So let's get a z-score. I know it's my target value minus the mean, all divided by the standard deviation. That's an S. Or you know what? Here's the other notation. I could do target value minus the mean this way over the standard deviation. I know I'm really mixing matching symbols here. Okay. So my target value is this many centimeters. That's my super tall person. My average value is what it's been all along, of course. Okay. And then my standard deviation, I have to use for a group. That's the last calculation we just did. Is that pop in right there? Right? Remember that? Because now it's a whole group of people. Okay. So what is this Z-score? Is everybody okay? Everybody okay? Okay. Ooh. Ooh. It's a much bigger Z-score than before. Huh. 1.99. Is that approximately 2? 1. I'll write 1.99. Okay. You guys see it's basically 2 standard deviations. Isn't that what Z-score means? 2 standard deviations. Okay. Let me show you guys how this maps onto these bell curves before we go to that Z table, because I have a graphical version of it here. Okay. So remember, here's for an individual, here's for a group of 5. You guys remember these 2 bell curves? Okay. So what's the chance that someone's really tall? Now, my original Z-score for an individual was 0.89. Is that it's a little bit less than 1, right? Okay. So on my graph or on my bell curve, that'd be right about here. And what's the chance that somebody is even taller than that? Do I have a I'm going to shade this in gold first, right? So for a single individual, you guys see I'm shading in gold right there? You guys see it gold shading? Right? That was what was it? 19%. Okay. Could this shaded in region right here reasonably be about 19% right there? You guys see it? Right. Right. But the same height, because it's the same target height for a tall person, right? On this now skinnier curve. Ooh. You guys see what I just shaded in pink ink right there? Right? Now you guys just told me it's going to be probably somewhere between 1 and 5%. Could this shaded in region be about that of this bigger bell curve or the skinny bell curve? Right. Let's figure out exactly what it is. It's Z table time. Z table time. I have a Z of 1.99. So here's 1.9. Oh, 1.9. That's right here. Bam. 0.9767. I'm going to round that a little bit to 0.977. Hey guys, 0.977. What does that mean? That means what? Does it mean 97.7% of people are shorter than that? Or I should say groups of blah, 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 right? So 97.7% shorter than. Okay. Now, one last detail is look very carefully. How is the question framed? Does it say shorter than or taller than? Does it say taller than? Yeah, taller than? How many people are taller or groups are taller than that? Okay. So that's percent or short is that, right? So what's the percent of being really tall? Shouldn't it be 100% minus the short people? Right, okay. Right. And what is that? Is that like 2.3%? Okay. And that's the answer to this box right here. Okay. Oh, remember you guys just conceptually a few minutes ago said this has to be probably somewhere between 1 and 5%. It sure is, isn't it? Sure is. Okay. All right. While you guys are checking your work, catching up. All right. Recap this concept. So, the first question, number 1, is the same as we've been doing last few days. Right. If you know the average and the standard deviation and a target value, you can get a Z-score for that target value. You can consult the Z table to get what percentage are up to that value, which the Z-score, the table showed 81%, which means how many are taller than that is 100 minus 81, which is 19%. Right? Then we put people in groups, which means that we're making this bell curve narrower. The average of the group is definitely tending towards the global average, right? And it's more often going to happen. Right? So what's the chance that somebody is super tall on an average of a group of people compared to an individual? Well, that's not going to be nearly as much. Okay? In fact, we just got this number right here to be about 2.3%. That's what we just got. So Z-score of 1.99, table said 97.7%. Would that be less than that height. So more than that height is 100% minus 97.7, which is 2.3%. Right, who has a question? Who has a question? Right, so everybody's good on their packet so far up to that point? Right, so everybody has that whole left side filled in. Right? All right, now here's where I'm going to take a pause and give you guys some analogous stories. And so hopefully this is clicking, but really drive this home here. So I got a story involving space aliens. Let's go into a flying saucer right here. Let's go inside this flying saucer. Get some space aliens here. Here's a little space alien, here's a little space alien. And they're talking to each other and they're observing Earth is in the background. So here's Earth. Right, get a little continents going. There's Earth. Right? And their job is to try to figure out something about how does human society work. And then you have to go back and report to their home planet and tell all about the humans. Right? But here's the difficulty is these space aliens, and we're the space aliens, right? We can't get too close to Earth because they'll see us zipping around in the flying saucer and everybody's going to freak out. So we have to keep some kind of distance. And we can see some things about how humans and human society works, but maybe not in a great level of detail, right? And one thing we can see is the heights of people, and we can see people walking around, and we can see them going into buildings, right? Now, say we line up some people. We've got some short people, got some tall people, right? We've got all different heights of people, right? All different heights. Right. But rarely is anybody 7 feet tall. I mean, there are some people 7 feet tall, but almost nobody. Right. Right. And as we're watching people walk around and go there, right? One of these is basically and say, hey, you know what? I think I just figured out something about human society if I watch them really closely. I think I hypothesize that they're playing a sport that I'm gonna call basketball. Right. And his alien friend says, oh, well, what is that? And what's your evidence for that? Right? And notice this is all going to be statistical evidence. This is probabilistic based. Right? And he says, well, my reasoning goes like this. Right? There's all different heights of people, but there's only a few people that are like 7 feet tall. But weirdly enough, there's a common event that happens where you might get like groups of five people. They're all like in that range, like 7 feet tall. They're all wearing the same jersey. And they're all walking to the same auditorium at the same time for the same like 2 hour span, right? Now we can't see inside the auditorium. We don't know exactly what's going on, but there has to be some impetus for groups of 5 of really tall people to get together and be in the same place at the same time. So that leads me to my hypothesis of I think there must be some game that exists such that it would be advantageous for, say, like a team to have really tall members. Maybe you have to reach up really high somewhere or something like that, right? And maybe they're competing against another team because I see another team of 5 people that's all super tall wearing a different color jersey, right? So you can see, even though you can't actually see inside the auditorium, you can take the statistical evidence and you can infer that basketball has to exist. You guys see that? Okay, because what would be the chance that 5 people walking together are all 7 feet tall? Well, if it was completely random, the statistical probability would be approximately 0. So if this is regularly happening, that would only happen if something like basketball exists. Hence, basketball exists, right? Now, what does this have to do with quantum mechanics? Now, there's a few tie-ins between statistics and quantum mechanics, but one of the tie-ins has to do with particle physics. So possibly by the end of next week, you guys are going to see this table. It's called Standard Model. If you ask a scientist what makes up everything in the universe, well, it depends what kind of scientist you ask. If you talk to a chemist, are they going to point to the periodic table and say, oh, everything's something off the periodic table, right? Now, if you ask a particle physicist, they say, well, like dark matter and stuff aside, actually, all those elements are really made out of protons, neutrons, and electrons. So maybe that's more fundamental. And oh, look at here. Do you guys see an electron right here? It says electron, right? I don't see protons and neutrons because those you can actually break into these quarks here. They're called up and down quarks. Right? And there's other elementary particles too. Right? Oh, I see photons. I see some kind of charm particle here. I see what's this? A Higgs boson, right? Now, guys, do we have photographs of any of these? Have you ever seen a photograph of a photon? Is that a thing? No, that's not a thing. It'll probably never be a thing, right? So how do we know that or any of these other ones exist? And this model was first worked out mathematically on paper by theoretical physicists, I think back in the 1970s, something like that. Right? But these particles have been experimentally verified just in the past about 20 years or so, a lot of these, right? By experimental physicists working at Atom Smasher. And the biggest one, the most famous one right now is called the called the Large Hadron Collider. So Large Hadron Collider, this is over in Switzerland. They have a huge synchrotron, and they're firing these atoms that they're protons, and they're getting them up to almost the speed of light. They're going like 99.9% the speed of light, and they'll get another one going the other way. And they'll smash these together. Now that particle collision is a really messy collision, and they can get some kind of data out of that, some kind of charge, mass, and spin data out of that, right? And then they run billions and billions and billions of collisions. And out of that aggregate data, they're able to say, well, this aggregate data would only show such and such numbers if these particular elementary particles existed that we predicted back in the 1970s. Right, you guys kind of get that? One of the analogies you'll probably hear a couple weeks from now, I don't have a video, I'll probably play it, has to do with if you ask a blind person, what does a piano look like? And the only evidence they have for what a piano looks like is they're going to roll a piano down a staircase, and they're going to listen very carefully as the piano rolls. Clink, 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 clink. Say, what object could have made that sound? Well, I don't know. Let's roll another one. Second piano. Clink, 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 clink. Well, let's roll a third one. What if you have billions of pianos and you're rolling down the billions of staircases? It's clink, 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 clink. Right? And after billions of pianos rolling down staircases, you say, they would only, in the aggregate, make those sounds if a piano looked like this. And then you get a pretty good model of what a piano looks like. Okay, that's a standard model. All right, so, all right, you guys ready to go back to the packet? So this example, number 3 and number 4 is pretty similar to what we did, number 1, number 2, except now we're looking at bottles of water. So you guys get to see us all one more time, right, and solidify some of the concepts. Number 3, suppose that the volume of a bottle of water was, now mine says 1,000 milliliters. So I have an X bar of 1,000 milliliters, and you guys have something else on yours. And I have a standard deviation of 4 milliliters. Okay. All right. So what's the expected volume of a random bottle picked off the shelf? Would it just be the average value? You just copy paste that right there. You guys see that? Right. Kind of like before. Right. Guys, suppose you picked a few bottles off the shelf. What's 1,000 plus or minus 4? Is that 996 to 1,004? Something like that, right? And anything between 1,000, between 996 and 1,004 should cover what percentage of all the bottles? 68, right? You guys remember that from yesterday? The 68 right here? Right, that's plus or minus 1 standard deviation. Okay, keep you guys on your toes there. Right. So what's the Z-score for a super filled bottle of 1,005? Ooh, super filled. So I'm going to take the target value of 1,005, subtract the mean, divide by the standard deviation. That'll give me a count of how many standard deviations. That'll give me a Z-score. Okay, so let's do that right now. So I got my target value of super filled bottle. Subtract the mean. Okay. Now, how super filled is this? It's a little bit super filled. This is crazy super filled. That I won the lottery and got the most filled bottle out of a million bottles. I only know that if I divide by the standard deviation. Okay, and that's going to be 5 on 4. Is that 1.25? I think. Right. My units are gone. Milliliters cancel. Right. Does everybody have a Z-score right now? Is everybody up to where I am? You guys got a Z-score? Just good. Right. Now, what does that mean? So that's the next question. What's the percent chance? What's the chance that the next bottle chosen, random bottle off the shelf, has a volume of that already overfilled volume or more? So 1,005, 1,006, 1,007, 1,008, and so on all the way up. Okay. Right. All right. So you guys ready to find that on the table? So I'm going to play out the Z-score, 1.25. And you guys know your Z-score. Probably different than mine. Okay. Go to the table. Here's 1.2, 1.20, 1, 2, 3, 4, 25. This number, bam, right here. Right here. Okay. So here's 1.2, and then scroll over to 5, 1.25. Mine says 0.8944. Is that? Okay. Okay. Now, that refers to the shaded region, doesn't it? Like how many bottles have less water than that up to that bottle? So I'll say the probability of less is 0.89. Well, I'll just round it to that. Is that okay? 0.8944, and just call it 0.89. Okay. Would that be 89%? Right. Now that's how many bottles have less than the overfilled bottle. So if that's true, how many, or what percentage of bottles have more than that? 11. Yeah. Isn't it just 100% minus 89%? That's where I'm getting the 11%. You guys all see that? Right. And to match up with this bell curve, remember the table tells you how much the bell curve is shaded up to that value. If that's 89%, then wouldn't this little white tail right here represent the other 11%? You guys get that? Right. So the table value tells you, well, in my case, 89%. Subtract it from 100%. That tells me how many have more than that. And that is the answer to this box right here. You guys got that? Okay. Everybody all right? Everybody doing good? Everybody doing good? Okay. All right. So number 4. Now we're going to put bottles into groups. Okay. This is quite a bit more realistic. Yeah, I think another example I've been using is, what if you work for a consumer protection agency? What if you want to test is there truth in advertising? And I'm going to grab a bunch of bottles, and if it deviates too much from the expected value, I can statistically say that there's something off here. Okay, or maybe not. Maybe there is truth in advertising. Right? Or could you guys match maybe like a bunch of different stories to this? What if you want to test for some particulate? Like, what if you do a chemistry analysis? You say, oh, what's the parts per million of, I don't know, like zinc or something, right? You could determine that too. Wouldn't that be all statistics? Right, good. Right, so we're just stick to volume here. What's the expected average volume for 5 bottles? Okay. Well, shouldn't that just be the same as the expected value for 1? And the same as expected value for a billion bottles? Right? Right. Now, but what's the standard deviation? Right. Now, here's where get the new concept for today. You guys remember we're going from a single bottle, which is this wide curve, to a group of bottles, which is a skinnier curve, right? Okay. So I need to take the regular standard deviation and divide by the square root of 5. So we have for 5 bottles. So I'm going to say standard deviation for a group is equal to standard deviation for a single bottle, which for me was 4 milliliters. Then I need to divide by the root of 5 to get for the group. Get this number right here. Oh, oops, milliliters. That still has the unit. Milliliters. Okay. So that is this number right here. Okay. Did you guys also get your standard deviation for a group? Okay. And notice it's smaller than it is for a single individual. Okay. I have 4 versus 1.79 milliliters. Okay. Okay. So what's the z-score for? Do you guys remember this overfilled bottle? Mine's 1,005 milliliters. Okay. But now I'm gonna have a group of 5. This kind of reminds me of like a group of 5 basketball players, and they're all super tall. That would not randomly happen, but it would if there was a sport called basketball. Right. So let's do this for these bottles. So it's the z-score on the bottles. Okay. So got my target value of 1,005, the average value of 1,000. Okay. Divide by the standard deviation, but now my standard deviation is for the group. Looks like that. Okay. So it's 5 on 179. Okay. Looking at 2.79. Right. So okay, now that's a unitless value because it's a count of how many standard deviations. Okay. Ooh, now right away, that's a pretty hefty z-score. Right? Because guys, that z-table that we're about to be looking at only goes from what to what? Negative 3.5 to positive 3.5. Right? At that point, you've covered almost the entire population. Guys, this is a z-score, it's getting closer to 3, which is getting pretty big. I'm getting pretty far out on the tail. Pretty far out on the tail, right? Right here. Here's what we're trying. Here's the graphical version of what I'm trying to find. Is how much this little skinny bell curve, how much of that tail did I shade in? Right. Now for the height people, it was like 2%, but for the bottles of water, probably something a little different. Okay. So 2.79. Let's go to the z table. Here's 2.7. 0.39 is 0.9974. So the percent or the probability of less is 0.997. Here, I'll just round it to that. 0.997. Gotta call that 99.7%. Is that right? Right. Straight off the easy table. Right. But the question is framed how many more? What's the probability of more? And guys, what would my answer be? 0.3. 0.3%. Okay. And that's my last box. Whoops, sorry, this was 2.79. Therefore, this was 0.3% would have more, right? Again, a group of 5 bottles. Okay. Okay, guys. Okay. I did forget to show you guys one more poster. So let's tie this back to particle physics. You guys remember Large Hadron Collider? We're smashing particles together, gathering lots of data, looking at it in the aggregate. That's how we're able to make sense of all these, determine the existence of all these elementary particles. Right now, what's the particle physics standard for determining a discovery? Because guys, remember in particle physics, your discoveries are probabilistic. So I can tell you guys it's on par with winning the lottery. You guys see this nice bell curve right here? You guys see this bell curve? You guys remember z-score? How many standard deviations are you from the mean? Here's my 68%, 95, 99.7, up to plus or minus 3 standard deviations. Right now, guys, what if you were to win the lottery? Would it be 1 in millions? Guys, suppose you buy one lottery ticket in your life. The chance of you winning is like 1 in millions, isn't it? Right now, let's bring that over to particle physics. What if scientists look at the aggregate data and they say, hey, it looks like we've discovered a new particle. What's the chances it's completely random and we haven't actually made the discovery? There's something in particle physics called a 5 sigma standard. So when particle physicists say, like back in the year 2012, they said, we finally have enough data to confirm the existence of this Higgs boson right here. That was the last one on this table back in 2012, right? That was because if the Higgs boson had not truly existed, there'd be approximately a 1 in 10 million chance of that being the case. Okay, so this is all probabilistic going on. Right? All right, so that should complete the whole packet. You guys have the whole packet finished? Double check, make sure your name's on it. You guys can turn that into the gray tray, and I'll start scoring those. And oh yeah, we have about 10 minutes left in class, right on schedule. We pause this recording and get you guys a quarter page here.